Today we will be looking at aromatic compounds on Chapter 17. Aromatic compounds are identified by following certain criteria from Huckel's rule. For aromaticity, it has to be flat and cyclic, fully conjugated, have 2, 6, 10, 14 or more pi electrons, or have an odd number of pi bonds, counting lone pair in p orbitals. For anti-aromaticity, it has to be flat and cyclic, fully conjugated, and have 4, 8, 12, 16, or an even number of pi bonds, counting lone pair in p orbitals. Any compounds that don't satisfy these criteria for A or B are described as non-aromatic compounds. Looking at the first compound, we can see that it is flat and cyclic, it is fully conjugated, and it has 2 pi bonds. With an even number of pi bonds, we can say that this compound is anti-aromatic. Now, looking at the second compound, we see that it is not fully cyclic with a pi bond outside of the rings, so we can already conclude that it doesn't follow any of the rules and that it is non-aromatic. Now, looking at the third compound, we see that it is fully cyclic, it is flat, and the oxygen has 2 lone pairs. However, one of the lone pair is sp3 hybridized, whereas the second lone pair is in p orbital. Therefore, it participates in resonance and it is part of the pi electrons that are there, which gives 3 pi bonds, where this matches Huckel's rule for aromatic. Lastly, looking at the last compound of the row, we see that the sulfur has 2 pi bonds, where the first one is sp3 hybridized and the second one is p hybridized, and the lone pairs on the nitrogens are sp2, so they will not be participating in resonance. So therefore we look at the pi bonds in the ring, and counting all the pi bonds, including the lone pair, we have 3 in total, giving this compound being aromatic. Now, looking at the next row of compounds, the first one, we see that it is already not fully conjugated, so therefore it doesn't meet any of the rules and that it is non-aromatic. The second one, as you can see, it is not cyclic. Even though it is fully conjugated, it doesn't meet the rules. Therefore, it is non-aromatic. Looking at the third one, it does have a positive charge, but it is fully conjugated. It is cyclic and flat still. And with that, it has only 2 pi bonds, making this compound an anti-aromatic with its even numbers of pi bonds. Lastly, the compound is fully conjugated. As you can see, it would not want to bend even though there are more than 6 carbons in the chain. And therefore, with 4 pi bonds, it has an even number of pi bonds, so it is anti-aromatic. Next, we'll look at our next row of compounds. And looking at the first compound, we can see that it is flat, cyclic, and fully conjugated, with the lone pair and the negative charge. So in total, we see that there are 3 pi bonds, which is an odd number, making this compound an aromatic compound. This next compound has 3 nitrogens within a ring, and each one has a lone pair. However, each lone pair is not in p orbitals, therefore we can look at the pi bonds within the ring. From that we can see that it has 3 pi bonds, which make this compound aromatic, as it is also flat, cyclic, and fully conjugated as well. The third compound, we can see that it is cyclic, fully conjugated, and has 4 pi bonds. Therefore, we would think it is anti-aromatic. However, this is an 8-carbon ring where it would be able to bend, and as a result, it would not fit the criteria of being a flat compound. Therefore, it is a non-aromatic compound. Looking at the last compound, we see that it is fully conjugated. It has 4 pi bonds and it is cyclic, but same as the previous one, it has 7 carbons and it would want to bend, therefore it is not a flat compound, making it a non-aromatic compound. Next, on our last row of compounds, we see this compound. It is fully cyclic, it is conjugated and flat, even though it would not want to bend. Therefore, it is an anti-aromatic compound. The second compound we see, such as previously, there are pi bonds that are outside of the conjugated system. Therefore, it is already non-aromatic, as it does not fit any of the rules because of that. And the third one is a bit tricky because at first glance it looks like there are no pi bonds at all, making it a non-aromatic compound. However, if you were to draw out the lone pairs and draw out the system, then you would be able to see that it is a fully conjugated system within a cyclic and flat compound, making this an aromatic compound. Lastly, on our last compound, it is fully conjugated, it is flat and cyclic. It would not want to bend and stay in that position. It has 5 pi bonds, making this compound an aromatic compound. Next, we have predicting the following products of the reactions. The first reaction, we see a benzene ring with an isopropyl, a methyl, and a tert-butyl, and we see that it is Jones reagent, and that will make an alkene to a benzene ring turn into carboxylic acid as long as they have a proton that it can donate. So you would see a proton that it can donate from the methyl group and the isopropyl group, whereas the tert-butyl group does not have any protons to donate, therefore it would not react with Jones reagent. And so the product would be carboxylic acids replacing the isopropyl group and the methyl group, leaving the tert-butyl group by itself. So the second compound, we have Kmno4 and water and heat, and this does the same thing as Jones reagent, where it has to have a proton connected to a proton on the carbon that is connected to the benzene ring, and with this one it'll cut off everything else including the alcohol, and you would get your end product with 2 carboxylic acids attached to the top and the bottom of the benzene ring where the old compound was. For our last reagent, can you tell that there would be no reaction since there is not a benzene ring in the reagent? Therefore, Jones reagent would not react at all with that compound. Next, we have synthesis problems, where we have to find ways to make the beginning reagent into the end product. So from here, we can add a Br to the end of the methyl group using NBS and heat. And from there, we can make the product in another step from the Br from using NaOH, which will make it into our product here as a primary alcohol. Our next synthesis problem, we can do the same steps as before using NBS and heat to add a Br to the end of the methyl group, and from there we can add in NaOH to make our primary alcohol again. And in order to add the propane group to the oxygen, we would add HgOAc2 with the propene at the end there and NaBH4, and it'll give you the end product. For our last synthesis question, we would have to make this reagent turn into the end product with a ketone. So from there, we can start with NBS once again, and it would add in the Br at the end of the methyl group. And then from there, we can use Grignards to create an alcohol, and the Mg would take away the Br, and the phenol would be a cation that would attack the bottom of the carbonyl, pushing the bond up to the oxygen. And using workup, it would give us an alcohol at the end. And lastly, if you remember from alcohol chapter 12, if you use PCC on a secondary alcohol, it would turn that into a ketone, giving us our end product.